So today I'm going to introduce you guys to the concepts of uncertainty, and we're going to go really fast through that stuff. So let's start talking about uncertainty. So the basic concept of uncertainty is, I'll just start straight into the concept of it. Say you have a scale and you have a paper or a string or something, and you're measuring the length of it. So say this is say this is 10. So what's the length, or where does this stop exactly? So a lot of people will say it's going to stop at 10.15. A lot of people will say, well, I don't have that reading, so I can't say 10.15. So basically, we would choose another value, right? So this would be like 10.1. Because 1.5 has no mark, so why would I say that? That's a logic. Another person would say, because I can't say 0.15, I can say 10.2 if I want to round it off to the closest value that I can see. So basically, you can get these different opinions about the value. And the truth is, they're all actually correct. And the reason they're correct is because of this concept, the principle of uncertainty, which says that you can't ever exactly have the perfect value that there is. So anyway, so it's the principle of uncertainty which says basically that you can't have an exact reading for the value, because even if I said this was 10.15, that doesn't necessarily mean that the value is 10.15000000 forever. So we know for a fact that we can't ever get an exact value. So what do we do? The best thing to do is, instead of going crazy trying to find the value down to the last atom, we kind of just say it's around this value, right? So it's basically the concept of uncertainty, and it's applicable to everywhere, anything we do. So one example of uncertainty would be if I ask Maksudul right now, how much money does he have in his pocket? How much money do you have in your pocket?
I don't know.
All right, so so you have something around
2,000.
Wow, rich boy, man, rich boy. Pocket 2,000 taka. So do you think you have exactly 2,000 money in your pocket? Exactly.
I said around 2,000.
Oh yeah, good game, good game.
Plus minus 100.
All right. So yeah, there we go. There we have Maksud saying something.
Weird
So. Yeah, that was a very weird flex. But that basically means if I pull the money out of his pocket, I might get anything from 1,900 to 2,100 taka. So that doesn't mean that if I get 1,950 or 2,000, he's wrong. However, if I empty his pockets and I see, like, oh no, my brother gave me some extra cash, and so now I have like 3,000, then his estimate was wrong. However, if his estimate was between these, then yes, that's acceptable, because he said plus minus 100. So this concept applies everywhere with every measurement, anything that we use. So the same thing goes along here. So instead of trying to go crazy finding the exact value, what we do is we write 10.1 plus minus 0.1. That's one of the fair ways of writing it. You can even write 10.15 plus minus 0.05. Please notice something really important right away, that the decimal places of the absolute uncertainty, this is called the absolute uncertainty, is always equal to the decimal places of the reading that we're taking. So if you give it to one decimal place, then you have to give the uncertainty to one decimal place. Very easy, very basic stuff. So, what about my pockets? My pocket's empty, man, empty. There's nothing in my pockets. So, moving on. So, 10.1 plus minus 0.1. So, basically, what happens is that the uncertainty in this value, you can write the value like this. This is called the absolute uncertainty, and this is the measurement itself. They have to have the same number of decimal places. Why? If I write 10.1, that basically means I know this value up to its first decimal place. This value in reality can be anything from 10.05 up to 10.14. Any value within this is 10.1. That's the reason I wrote 10.1. So, Shahryar Zaman, no MCQs today? No, not really. Let's get this concept done, then we can ask MCQs tomorrow. We'll do MCQs on uncertainty tomorrow. You can follow that up. But to do good in that, you'll have to listen to today's discussion. And maybe practice a little bit of uncertainties by yourself, so that when we give chocolates tomorrow, we know who to give them to. We'll choose a student of the day tomorrow. So 10.1. So what happens is basically, if I was to write 10.10, that is totally different compared to 10.1. If I write 10.10, that basically means that the value is somewhere from 10.95 to 10.104, right? Oh, 10.095, my bad. There's a 0 there. So the value is within this. So as you can see, the range changes a lot just by adding this one decimal place. So it actually means something. If the value is like, say, 9.0 and the value is 9, just because on the scale, if it's 9, that doesn't mean you should write 9. You should write it to its proper number of decimal places, 9.0. So that's basically how we represent the decimal places. It's really important that you make that, straighten that stuff out, because people do miss out on a lot of marks just because of this. Right. So moving on. So going back to our original example, say, let's simplify it. So say we can write 10 plus minus 1. So now what happens is, we can represent, this is called the absolute uncertainty. Absolute uncertainty. So if this was in centimeters, so basically this means the value is anywhere from 9 to 11 centimeters. And on the other hand, what we can do is, we can represent the uncertainty in different ways. Whenever I mention the absolute uncertainty, I must mention the unit with it. If I don't mention the absolute uncertainty, the other thing that I can do is I can write it as fractional uncertainty. So if this was, say, del x, and if this was x, so just writing del x is this. And then I can write del x by x. That's basically fractional uncertainty. So if I was to take fractional uncertainty, if I was supposed to write that, then, if I was to write that, then this value would become 0.1. An important thing is, I can't write the unit anymore because the units just got cancelled out as a ratio. And basically, this value just stays as that. It's a ratio, but I can't express my final answer in a ratio because it doesn't make any sense. I can't write 10 centimeters plus minus 0.1. 0.1 what? Percent, centimeters, we need to know. So the next thing that I can do is I can take the fractional uncertainty and I can multiply it with 100%. So that's going to give me, like, 0.1 into 100% is 10%. So if I write 10%, that does make sense. What's going on? That does make sense. It makes sense in the way that basically I can write 10 centimeters plus minus 10%, or I can write 10 plus minus 1 centimeters. I can't write 10 plus minus 0.1. That makes no sense. Right, this is basically the representation of uncertainty. This is how we show it. Now the important thing is, how do you observe its propagation? So the next thing is, so we have the concept of absolute uncertainty figured out. So it's going to be x plus minus del x, right? So that would be, say, 10 plus minus 1 that I just said. And say we take another value, say y plus minus del y. So say that's what, 15 plus minus 2?
Yeah.
All right. So now, if we add these values, say we want to do x plus y, what we do is we add their absolute uncertainties. So that's going to be, because the longest value that this can be is 10 plus 1, which is 11, 15 plus 2, which is 17. So, yes, you're learning physics. Congratulations, Naren. Let's keep going. So basically it's going to be 11 plus minus 17, which is basically 28, right? That's the highest value that x plus y can have. And the lowest value that it can have is 9 plus minus 13, right? That's equal to how much, Maksud, before you fall asleep? So 10 plus 15. So your answer has to have these within its range. So how do you do that? You basically use this equation, x plus y plus minus del x plus del y. So you add their absolute uncertainties. So that would basically mean 10 plus 15, 25 plus minus 3. So 25 plus minus is the 1 and there's the 2. So plus minus 3. Interestingly, if you write that 25 plus minus 3, it considers both of these values. 25 plus 3 is 28, 25 minus 3 is 22. So boom, there you go. Really easy. Mind blown, yeah? Second possibility is x minus y. So in x minus y, what we do is, so here's the place where people make mistakes. So the biggest difference between the two would be if I subtract, say, instead of x minus y, to avoid negative values, let's write y minus x. So the largest of this minus the smallest of this, which is going to be 17 minus 9, which is equal to 8. And the smallest difference between them is going to be 13 minus 11, which is going to be equal to 2. So what can I do here? Very easy. Again, uncertainty always increases. We can say y minus x plus minus del y plus del x. Never, ever, ever think that uncertainty decreases. It's always going to increase. All right, we have a question here. Is it necessary to display absolute uncertainty in one sig fig. Is it absolutely necessary one sig fig? No. You show the uncertainty to the same number of decimal places as the measurement itself is, the true value is. And how many values that's going to be depends on the value itself, all right? So it's going to be like that. Yeah, that's basically the point that would be your question. So, moving on. So y minus x is, you're going to have the uncertainty increase. Uncertainty never decreases. We never subtract uncertainties. It's like playing Chinese whisper. So like, if Maksud hears from someone that today we're having pizza, and then Maksud, but the person's a pathological liar, say, and then Maksud is being himself another pathological liar. If he comes and tells me, like, do you know they're serving 100 burgers down the street? So this uncertainty is never going to decrease into its original thing again, right? It's going to turn into something weirder and weirder. Everyone's played Chinese whisper. So it's a similar concept. Chinese whisper is an idea of uncertainty, and uncertainty always increases. It's never going to go back to something. I remember once, so one of my friends did Chinese whisper, and she started with "Man U sucks," and by the time it came to the other end, it turned into someone's girlfriend sucks. So that's never going to go back to Man U, right? So basically, well, it might go back to Man U, you never know. Pizza, yes, we tried ordering pizza today, but Maksud's food panda wasn't working.
Now they stopped taking orders after 10, I guess.
Tufan.
Yeah.
So yes, moving on with this, del y plus del x. So you always add uncertainty, it never decreases. So yes, y minus x is going to be 15 minus 10, which is 5, plus minus, you add the uncertainties again, 3. Did this light just go out?
Yeah.
Why?
Fix it.
Oh, there it is, back. It's back. We're back. So yes, so it's going to be 5 plus minus 3. So basically this 5 plus 3 is 8, 5 minus 3 is 2. So we got them covered again. So that's basically how it is. That's how we have these values working and how they operate. So uncertainty always increases. So the addition and subtraction, we can nicely put it into one concept. The concept would be, no, we didn't have pizza initially, and we were wanting to have pizza, but we missed out on it. So instead of that, now we have all time, when there's only one piece of all time left, sadly. I'll have it later. So yes, moving on. So we can put both these into the same equation, which is basically this and this formula, basically. And the rule would be, during the addition or subtraction of values, you always add absolute uncertainties. All right? These are absolute, so you add absolute uncertainties. So there's a similar law that you could follow for multiplication and division, which would be, Maksud, can you tell me?
What?
During the multiplication and division of values,
Oh, we add the percentage.
Percentage or fractional uncertainties. So we need to write equations for that. So x into y plus minus. So we'll write the fractional uncertainty of x, right?
Changing x by.
Del x by x plus the fractional uncertainty of y, del y by y. However, as I previously mentioned, you can't just leave this as a fraction, right? So what do? It's going to be basically, you need to take this value and you have to multiply it again with this value. Where is this coming from? Basically, del x by x is fractional uncertainty. So to make it turn into absolute again, what should you do? You multiply it with x, so it turns into absolute, right? So the same logic happens here. Basically, whatever fractional uncertainty you get, you need to multiply it with xy into xy, so that you get it in its absolute form. Similarly, for division, it would be x divided by y plus minus del x by x plus del y by y. Going back to the Chinese whisper thing, uncertainties never decrease. So similarly, you take the absolute uncertainty, you multiply it with your n value so that you get it in its absolute form. Fractional into this will give you absolute. So that's basically how we work with uncertainties. So we can extend this equation formula and come up with a few other interesting things. For example, say, what if it's x into x, or basically x squared? So it's going to be x into x plus minus del x by x plus del x by x into x into x. So basically you're multiplying the uncertainty into 2. So we can simplify this into x to the power n plus minus, basically these are 2. So you write n into del x by x into x to the power n. So if it's cube, this would be 3 times. If it's to the power 4, it will increase by 4 times. So that's basically what we get. So based on this, for example, we can use this to do simple stuff. For example, if v has an uncertainty of 3%, what's going to be the uncertainty for v squared?
6.
6%. Easy peasy. So stuff like that. Or like, if L has an uncertainty of 5%, what's the uncertainty of L cube?
50.
15%. There you go. Or if M has an uncertainty of, say, 8%, what's the uncertainty of root M?
21.
What?
4.
Why do you 4%? Right. There's a few important things that you have to keep in mind. Say, for example, you take a circle and you measure its diameter. So you take the diameter and you measure its uncertainty. So say the diameter has a percentage uncertainty of 10%, and that translates in an absolute uncertainty of, say, 3 centimeters. So if you needed the radius from here, half of the diameter basically, then the percentage uncertainty would remain the same. The percentage uncertainty would be still 10%. However, the absolute will become half, which is basically 1.5. So yeah, let's write 3.0 here to make life easier. So this would become 1.5 centimeters. So this is how you deal with these uncertainties. So these are the basic concepts of uncertainty. And please always remember, the most important thing is the number of decimal places of this must be equal to the number of decimal places of this. Instead of this, if I was to write 10.0, then I must write plus minus 1.0. I can't write anything other than this. Nothing more, nothing less. And other than that, in uncertainty, there are certain devices which have an uncertainty. And going back to the scale thing that I was saying, so uncertainty is going to be, both are correct, by the way, as I was talking about here. If you take the smallest reading to be uncertainty, that's all right. If you take half of the smallest reading to be uncertainty, that's also right. Both of them are accepted in the scheme. And always, whenever it's a device which takes 2 readings, for example, if this is a scale, obviously it's taking another reading here. So say if it's 8.3 plus minus 0.1, and if this is 10.1 plus minus 0.1, so the uncertainty in this is going to be 0.1 plus 0.1, it's going to be 0.2, right? So it's 10.1 minus 8.3, blah, 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 and then you get your answer 1.8 plus minus 0.2. So yes, these are the basic concepts of uncertainty. You need to practice these things to be, oh, the score changed.
Please.
Oh, man, it's 1-1 at 72 minutes.
Man.
Things aren't good. Things are not good.
One job.
Now they have another job. Parvana. Right, guys, any questions from uncertainty? Tomorrow we're going to be doing some question papers from uncertainty. It's going to make life better and easier for you guys. But other than that, if you have any questions, please ask. Please feel free to ask anything that you would want to.